fly through it and probably wouldn't have any problems. There's a lot of work to be done in that area, but it's one of the key concerns, and most of the money in this program is going to that area right now. Also, they're thinking of building the receiving stations out in the desert areas or out floating in the oceans and so forth, and then connecting them with probably a 70% efficiency rate, which is very, very good, into the normal grid systems. One of the solar sats, once we get into production, will cost about as much as a reactor does on Earth. It doesn't have the radioactive waste problems that we do with reactors and so forth. But it's a good observation and a real good question. The question is, would beaming the solar energy, the microwaves, increase the temperature of the upper atmospheres and so forth? I don't know that for sure, but I do know that there's so much heat generated from normal processes to create energy that they're much more worried about that than they are about energy from space coming down. They might even do some of these in polar orbits and do some reflection of the energy waves and so forth. But that's about a 20-year program before they could actually build a test model of it. Yeah. I'll get back. Go ahead. Yeah. Pardon me? Oh, they're here. Hi, guys. Where's Shelley? Hi, Shelley. How was dinner? Let me answer a couple of quick questions, then I'll introduce Fritz. The question was, are there some new materials being developed? And it's a definite yes. There's been a tremendous amount of materials and scientific research that's been done for our space program, and we're just now beginning to see a lot of those applications come into industry and even architecture. Ray Cappy, a year and a half ago, was involved with the NASA Technology House and did a tremendous amount of research into new kinds of materials and bonding techniques, materials that don't off-gas or fireproof, a variety of things. And that relates not only to materials, but processes and chemistry and technologies. We've got a tremendous amount of new methods and ideas and things from the space program, so I think it's very valuable. And you had a question up there again? Do I see any utopian? Not really. I don't think there is a... Well, I don't personally believe in utopias. I see humankind as an evolving species, always striving and trying, and I hope we never get to a utopia. I hope we continue to improve the world, which I think we're doing in a lot of ways. As to what we learn from these type of projects, we learn from everything, and it's really good to have a means of comparisons. I'm sure some of these large space stations will have their own unique governmental systems, their own social orders, and there's a lot of means for testing things in space that you cannot do down on Earth and so forth. But it may turn out that the sociological advances through these large space communities are far greater than the technological advances and so forth. Just like in the last 30 years, civil rights, women's movement, all those kind of more consciousness-raising things have been more significant, I think, in our society than even the technologies. In fact, our technologies goes faster than we figure out how to use it properly. But let me introduce Fritz now. What do you guys have for dinner?
Hamburger.
Yeah, sire. Okay. I'm very pleased that Fritz Runge would come, because he's really a perfect person to talk to us as an aerospace engineer talking to architects and so forth, because he's, of anyone I've met in the industry, sensitive and interested in our interest and discipline and our concepts and so forth. And Fritz has been very helpful to me and my companies getting going, and as far as I know, this is probably a bit of a historic lecture and exhibit, because it's the first time that we really are going to be introducing the concept of outer space architecture to the profession. A few of us have talked about it, and we've had a few seminars, but now we have a well-known speaker and also an exhibit, which I hope everyone comes and sees and talks about. Fritz has an interesting background. In 1949, he graduated from General Motors Institute of Technology. And then he spent several years working as an automobile body designer at GM and Cadillac. You developed those fins on the Cadillac stuff, right? Okay. From 1951 to 1962, he was an officer in the U.S. Air Force, and for several years had the opportunity to work with Wernher von Braun, who's really one of the fathers of our space program. A very brilliant man. And he was also a deputy director in the Air Force of the Air Force's weather satellite program, which has been very, very significant throughout the world, our weather satellites. In 1963, he joined McDonnell Douglas Aeronautics and is presently with them as the director of Advanced Space Payloads. Well, he's the Advanced Space Payloads Program Manager. Okay. And McDonnell Douglas tends to have lots of long names. But what that really means is that Fritz was involved from the day one when it comes down to thinking about realistic space stations, and was heavily involved in the design and planning of Skylab, and has been involved in Spacelab, space platforms, and is now helping to coordinate McDonnell Douglas's efforts, and they're really the most advanced as far as I'm concerned in terms of sensitivity and overall picture of what a space station is. He's directing that basic program. And I'm very pleased to have you here, and thanks for coming.
Thank you very much, John. Let me apologize for our tardiness. We had good intentions. We were here at 6 o'clock, and we solved many of the world's and architectures and space problems. Probably too late to even get the proper start on dinner, and that's one of the reasons we're late. But let me also start by saying that I appreciate very much speaking to a group that has the apparent interests and the background that you folks do. It's very easy for those of us in the business to be enthusiastic about the space business, particularly the manned space business, because a lot of us have been working in that arena for some time. And very recently, the President made a very positive indication of a new initiative in this area after many years of hot and coldness on the part of various administrations. But we also feel that as far as the image of the country is concerned and establishing our technological leadership, it's really an imperative as much as being a new initiative that would be a nice thing to do for our country because of the competition that we're obviously in with other countries. As I'll indicate in the briefing, the Russians have been doing what we propose to do now in the early 1990s. They've been doing that since 1971. And it seems to us that when there are these adversary relationships in the world, that there really isn't much of a question or debate as to where this country should stand. And I hope that this present initiative on the part of the administration sustains. There are obviously a lot of other fights for the money. We have large deficits and what have you. But certain things seem to be in a situation where their time has come, and the space station seems to be at that particular point in the juncture of the history of this country. I'd like to have you join me on sort of a journey of vision, if I might have the first slide, please, of the potential of a new dwelling for Earthlings in the universe that we live in. I'd like to have you join me in a little bit of a historical view of where man has been in flying in the higher reaches of space and where he might be going, hopefully in the next decade or so and the decade beyond that. This is a new dwelling place where a few select pioneers will be able to experience and work hard in an entirely new environment. And as John has just recently showed you, there are some even grander visions of more and grander and more expansive kind of things to be done in space. Obviously bridled by the amount of money that will be spent on that, but certainly not bridled by ideas. There are many things to be done in space. There are many things waiting for this country to be done in space involving men and women. We're really only hampered by the lack of funds and the amount of funding that can be put on these projects on a year-by-year basis. They are expensive to a degree, but when compared with other programs in the country, they're really quite small when you look at the productivity and the types of impact they have on the economy and the type of competitiveness that they create in our technological war, literally, with other countries. When you look back at where this country has been over the decades of the past, there was never a question as to the prominence, technological prominence of which country. It was always the United States. Now we find ourselves daily, and I with my children, sometimes to my chagrin and sometimes a little shoulder shrug, find that we no longer can say that we have this technological prominence. I like to feel what we've done with space, that we can maintain that prominence, and the space station has got to be that next step so that we can maintain that leadership. I also appreciate particularly in talking to a group that is architecturally oriented, because in fact we do use many of the basic practices and approach that you do in serving the interests of the payload community, understanding now the space station is a carrier vehicle. The payloads are our customers. The payloads are our clients. What they want to do, the accommodations they need, the interfaces they create with the carrier vehicle are the important initial requirements for us, much like you in architecture list down the needs, wants, desires of the client, and then begin from there. You obviously inject your own knowledge and superimpose that on top of what is needed, come up with a combined vehicle. Your client doesn't always understand what it takes to fight the weather, protect from the weather, to integrate the utilities, to properly create traffic flow in a household or in an industrial site. So you inject this over and above his basic requirements. We find those same situations exist when we confront many different scientists who want to do everything from testing and performing experiments on small animals all the way up to taking large diameter telescopes and many, many different kinds in between that entire range represented by those two extremes. So we have a set of clientele as diverse as you architects will ever have, and we have to satisfy them so that they are in fact in a position to create good science, commerce, or technological progress, will want to come back, will encourage their compatriots to want to fly in space station and not go away and say, oh, what a drag, you're cramped, you can't do your research, so let's do it in an unmanned mode, or let's do it from the ground, let's put more money into ground telescopes, make them larger, or do it from aircraft and what have you. So we are in competition with other modes. There are unmanned worlds and unmanned spacecraft to be flown. So I sort of looked here in this rather stylized, and you understand now that the engineering kind of artwork that you'll see here is a step shy of what I jealously look at a lot of architects beginning their presentations with. We use view graphs and not slides. I'm envious of the more or less, I should say, a little more feeling kind of introduction to your subjects that you have, because you deal with people on a more emotional basis trying to satisfy their needs than we do in engineering. In engineering, we satisfy specific detailed requirements mostly. You have to follow detailed requirements also, but we follow them probably 99% of the time. We do not have to satisfy anyone's aesthetic interests. We seldom have to compete for design lines or design impressions. You do, and that's what makes the world a great and interesting place. It's not quite as sterile as basic engineering. So I won't have a lot of the fancy slides and colorful slides that you have, but I hope that we'll get this message across. Next view graph, please. This then is an example of what we're talking about when we say space station in the early 1990s. This particular concept was developed under a study I ran for NASA a year ago, and it represents not an early version but a more advanced version of the space station, which probably begins with in the upper left half of that particular configuration. Later on, the third or fourth year, we would add major outside construction capabilities that you see in the lower right of the scene here. The lower right at that particular location is showing the construction of a 20-meter telescope, which, of course, you understand in low Earth orbit, we have a much more fantastic, less occluded, less clouded view of the stars and the heavens than we do on Earth. That's the reason we want to take large telescopes into Earth orbit, but they can't be taken up in one piece. There you see a 72 mirror face unit that is all assembled and hopefully is designed and engineered to operate as one piece of glass with little actuators under each one of those 72 1-meter mirrors. A heck of a job to assemble, a rough job to calibrate, but that's the intent of NASA, to fly something like that in the late 1990s. So with this then, a goal of a station that you see probably around the 1995 time period, let's take a look at really where we are and why we're there. If I could have the next slide, please. Here you see a view from orbit of the Hawaiian Islands. Started off as a colored picture in a beautiful book. I'm sorry I don't have it represented by anything but a black and white, but black and white sometimes gives you drama. There are those of us that enjoy black and white photography even more than color. But that wasn't the reason. I'm sorry for this being such a poor quality image. This is a view you don't see too often from Hawaii. You usually see it on a map and stare at the islands and dream about your vacation. But it gives an indication of a broad expanse of ocean, which, whether you like to believe it or not, we really know very little about. Oceanographic studies from orbit have been probably the least funded. An oceanographic satellite lasted about 90 days here about 4 or 5 years ago and unfortunately died in orbit. And the oceanographers are looking forward to a tremendous increase in study in various frequency bands and various telescopic looks of the ocean, measurement of the currents and the temperatures and the thermals and the gradients and what have you. The military is also very interested in it for a lot of obvious reasons, because a lot of the wars of the future and a lot of the threats and the defense will be from ocean surface vehicles and unfortunately under the ocean as well. So this is the kind of view that we're looking for getting, not just for a nice view to be seen out of a port or a window, but the same view to be covered by many instruments for science, for the military. We can't say that the military is behind the space station right now, but they have many reasons for those choices. And with all of the activities that the military has in space, there are a lot of us that feel that they eventually will certainly do technology testing on the space station, but that's a private opinion. But let's take a look at what made this all possible. If I could have the next one as an overlay, please. Would you make that an overlay? No. With the one I just had before that. I thought I was going to be flipping my own charts, so I'll have to excuse a little lack of humility. Sometimes have that view also when you're up there. The whole story behind the utilization of space is access. The whole story behind the utilization of anything that is remote from where most of the people happen to be in world history is access. The Phoenicians made access to the Mediterranean, the British Isles, mysterious African ports that people barely knew existed, and made a tremendous leap in trade, mostly to their own benefit, and governed trade for centuries because they were brave enough to go out and make access. Columbus obviously made access to the New World, and as did a lot of other explorers. We made access to the West by various means of transportation, and then finally by rail. We had access to these new spaces, and we capitalized on them. The shuttle has made access to space routine, and hopefully the space station now will capitalize on that. So we find as human beings, whenever access has been made, someone or several of us will always exploit it, capitalize on it, and it doesn't take human beings long to take full advantage of wherever transportation or some mode of locomotion can get you there. And the space station, of course, now will open up this entire new vista of things to do on orbit. If I could have the next slide, please. That same access goes looking the other way, not just down at the Hawaiians and the islands and the Earth, the stars themselves. Astronomy has the greatest political clout of any science in this country. More money spent on astronomical science, more appreciation on a part of the public, more broad millions spent on university research at various astronomical made that will frustrate general sighting of the astronomical targets. So Many of the interests in space are for looking out in infrared, invisible, far UV, X-ray, and what have you, a whole raft of frequencies, all requiring different telescopes, all involving dozens and hundreds of different scientists throughout the world. Next slide, please. What is the history then of space station? Early in 1960 and probably through the 1970 period, there were a variety of studies on the part of NASA and a little bit on the part of the military to look at 4 to 6 man space stations. Our company happened to win the first space station mock-up contract from the London Daily Mail newspaper. In the late 50s, they put out an RFP, and I think it was Boeing and ourselves competed for that. And we won a contract to build an elaborate mock-up, which was on display in the offices in London of this newspaper, to show what was in prospect for man in the future. Since that time, our company has had an involvement with every major NASA space station study contract. And we built Skylab, we built the Air Force MOLE contract before it was canceled. We advised the Spacelab consortium in Europe during the 70s, and Spacelab flew recently. So we've had a long and dedicated involvement in having man in space for long periods of time. Now the interloper in that was the access means. When NASA saw this tremendous potential in space, they concluded they could not get there with the Apollo configuration, which of course was this giant Saturn vehicle, all the parts of which fell in the ocean each launch. They had to have a reusable capability. So they developed the shuttle vehicle first. And one of the main reasons for the shuttle was to act as a 90-day, 3-month shuttle vehicle to a space station, which hopefully would succeed it, and which is now the general plan. 73, Skylab flew, had 3 visits and up to 85-day residence, and eventually, as most of you know, came down because the sustenance was not incorporated, because we felt the shuttle vehicle was coming, which would open up a new era of modular space stations as opposed to one giant large vehicle. Since that time then, a flock of studies were accomplished, and here and there the space station was on the brink of development, never materialized until in January the President cited it as the number 2 objective. I believe he had something like 5 or 6 objectives for this company and country in the State of the Union message. And now it remains only to be seen as to how much money will be put in it this year, next year, aimed at 1991. It's actually slipping a little bit now since this chart was made. 1991 launch. Understanding now 1991 is a good possibility we'll have a space station. The Russians have been up there since 71, and they've recently been escalating their vehicle to grander dimensions, already have weapons on the vehicle for a number of years, and are doing very sophisticated and openly, avowedly military applications, and we are still studying the problem. So we're looking forward to that being a forcing function from a technological and image pride standpoint. But again, those thoughts are great, but when you're vying for funding within the Washington scene, a lot of other emotional issues come into the budget picture. I won't repeat what the Russians have been doing. I think the chart stands for itself. Next slide, please. This is a recollection for you of what Skylab looked like. Actually a grand vehicle, 22 feet in diameter. We had enough volume above the spacious compartments, eating and bathroom areas, to do major locomotion experiments. There was a jet shoes experiment in which the people actually could move around and do major volumetric excursions within the upper, literally a small gymnasium up there, which we would love to have in future space stations. But unfortunately, the shuttle cargo bay is only 15 feet in diameter. And all the pictures you'll see of space stations from here on in will have that unusual uniqueness about each one of the modules of being 15 feet in diameter, the way Spacelab is now. Major Apollo telescope mount, a solar science research facility mounted out at the outboard in between that cruciform set of solar arrays, took the knowledge of the sun, which is so critically important to everything that happens here on Earth, just light years ahead in data and understanding and the effects on the atmosphere of the Earth and what have you. So there's a major benefit from just that one major experiment on board. Next slide. Spacelab flew recently. Very successful. A great credit to I think, 11-member consortium of European countries that involved everyone from Spain to Austria to Germany. Germany had the largest portion. I think the Italians were next, something like 50, 20%, then the French or what have you, British and whatever. They're all involved and got together in what was imagined to be probably a Tower of Babel kind of an operation that would fall apart because of lack of communication. They did a great job. We helped them in certain areas as advisors and consultants. We won that contract separately as a company, but they built it and they literally did it all and deserve the credit. European consortium put up $1 billion, 1 billion, what do they call it, 1 billion counting units, roughly equivalent to dollars. The Europeans hoped that this country would buy more than the one module, which is now available for flight. They hoped that there would probably be 3 or 4. That has not happened because the shuttle took considerable money, and there are a lot of money's had to be put into payloads and what have you. But the Europeans are still now, despite that, interested in participation in space station. And NASA is now grappling with how the Europeans might be involved in space station. Conceivably, they could take a Spacelab, outfit it for longer flight than the 7 to 10 day flight on a shuttle, and plug it into a space station. Germans are already planning to fill a module with their German experiments alone and for a space station utilization to show the enthusiasm that exists in the rest of the world. To talk about competition, most of you probably know the Europeans have a consortium vehicle called Ariane, which is a serious competitor, launch vehicle-wise, to our American shuttle and our company's Delta launch vehicle. So if you don't believe that competition enters into what goes on in space, you can look very quickly to the commercial world, which finds situations such as American companies flying commercial communication satellites on European vehicles. And the Japanese are not far behind. They have an N vehicle, which now has a major capability and prospect for geosynchronous operation, which is where most of the commercial communication satellites are. So we might be looking to the east and to the west for competitors now, as opposed to just to the east in the launch vehicle business, let alone the commercial services or scientific and technological experiments. This then is Spacelab, just begun, a long and fruitful series and prospect for it, but only flies up as long as the shuttle does. Therefore, we have this yearning to go many more weeks and months longer than that. Thus, we find the concept for a space station developing in our minds. Next slide, please. This is the interior of Spacelab. Probably a good image of what the interior of a space station module will look like. Remember the 15-foot diameter constraint of the cargo bay? Once you make that cylinder and want human passage and operation in between, you'll find yourself with your equipment on the outside, most likely. Certain passageway and maybe even some experiments in the middle of the floor as is shown here. And this probably will be found replicated in a space station scene maybe 5, 6, 7 years from now. So it's a good image. The Europeans could even fly something like this and plug it into the space station as a plug-in module. Next slide, please. So we see in an overview fashion then in the early 1990s, we're looking forward to not just the science or technology operations in space, in a space station. We're looking to specific commercial utilization. Our company has a joint venture with Johnson & Johnson in the pharmaceutical world for the use of a continuous flow electrophoresis separation of cells for pharmaceuticals. Very high demand, very, very expensive, very high cost to low weight items, and ideal for a situation in space station. Space station provides a zero gravity, which other things would apply to, various exotic materials and what have you, but pharmaceuticals and lightweight items with high cost are the things that really pay off in a space station. And I think you'll find that pharmaceutical production is in prospect for a space station. We've already separated live cells and some simulated cultures in earlier shuttle launches that you may have read about in the paper. So that prospect is there. Obviously, looking down at the Earth, its resources, and the Earth environment from that view is a great application of the space station, not the least of which is the ocean one that I mentioned, who feels like sort of a forgotten science from a space standpoint. Next one, please. Let's escalate in time to the late 1990s. Here we find several significant additions. Now the vehicle takes on a literal space base operational mode where we can launch vehicles to geosynchronous orbit, 20,000 miles in space, understanding the space station is down in several hundred miles altitude. Instead of launching everything up on the shuttle and out of the shuttle, we will use launch vehicles that are based on the space station. We will only bring propellants up from the ground now. And we'll be able to use that as a launch base to deliver and to service things that are in geosynchronous orbit. Also in that time period, we'll probably incorporate the flight of a unit that's called the platform over there on the far right of the screen. The platform is for those payloads that can't stand the shake and the rattle or the effluence of a manned vehicle. And that could be certain instruments, infrared instruments, certain visible region instruments that want a very quiet. They work in 1 arc-second pointing accuracy, and obviously they can't stand the impact of a man who's floating across and bumps into a wall, or someone who coughs, or animals that move and shake the vehicle. So they will want to be off on a co-orbiter vehicle, and that is called a space platform. And specifically for those reasons of service of separate operations, but yet serviced from the space station by little scooters that go over and replace propellants or exchange experiments and that type of thing. Again, a close-in operation using the space station as a base of orbital operations as opposed to bringing everything up from the ground with the shuttle. The shuttle schedule is getting very filled traffic-wise. So the space station is actually a relief to that operation by supporting things from orbit, from an orbital point of basic operation. Next slide. We look into the year 2000 and beyond. We find that we continue a lot of these various operations in a much more advanced mode in most of the ones that we started early, but we actually start to look to the space station as a lunar support base. The president told the NASA when they proposed the space station, "You're not thinking big enough. Tell me in what light the space station should be developed. Not as an end to itself, but to the support of some grander objective." He didn't tell them what, but the lunar operation, the Russians we know already have major designs on lunar operations. You'll see some lunar mock-ups and illustrative work here at the SCI-Arc display a little bit later, I'm sure. But lunar operations are in prospect. A satellite that goes around the Earth, and the Earth that has so many complex operations that require a military advantage of some off-site base or surveillance advantage is just too lucrative a spot from a military standpoint alone to stay there unused for very much longer. And the space station would be an advantage there. Next slide, please. This is a picture of the space platform, the vehicle that flies unmanned but is shepherded by the space station. Flies maybe 20, 30 miles away from the space station, and flight mechanics and physics principles being what they are, whenever you're in a different orbit, of course, you begin to fall behind or move ahead or fall below your companion vehicle. But it's a repeated process because you're basically playing with the basic laws of nature. So there's a scheme whereby we would have this vehicle slowly change its position around the vehicle in an ellipse. When we complete half the ellipse, we would use propulsion to elevate it to its original position, and then we would track around in that semi-ellipse flight mode again, and probably take several days to go through that excursion and then be escalated up to its original position. So look forward to the space station not being alone, but having an off-site facility for those payloads that do not want to be on the space station, but serviced by it. Next view graph, please. I believe we have two on top of that. Are there two separated? No, I'm sorry. Are there two stuck together there? Yeah, I believe so. Thank you. The other one first, please. everything that is on the space station comes up by the shuttle. The shuttle will then have to be, and here's where architecture comes in. As you look at an industrial facility or a high-tech facility, and you have frequent services coming into one point, you have to make sure that the entrance corridor, the operating envelope, and the service flow, the traffic flow of operations that take place during that logistics visit, in fact, are efficient. Now, generally, the visit of a vehicle like this is a major perturbation to the operation. Certain scientists will be brought up new, others will go home. Their equipment will go home. There's equipment that comes from the inside and is brought through tunnels into the shuttle. There's other equipment that is taken out with that large crane, taken out of the exterior cargo bay and loaded onto the space station. Sometimes we can see that we have to take off payloads on the space station, put them on a parking spot, take the unit out of the cargo bay, put it in the original position of the other one, and then take the other one and put it into the cargo bay of the shuttle. So we have this grand game of manipulation that goes on the outside, while inside, in what we call an IVA mode, intravehicular activity mode, the astronauts push these little units that are being replaced by others when the scientists or the technologists or the commercial people are exchanging payloads. So you can see the shuttle comes up. Another problem we have with the shuttle, a little social physical problem, is that it has major effluents. Its exhaust rockets for approaching the space station give off exhaust gases. Well, anyone that's sensitive to those gases, first of all, will put hatches over the optics or what have you, and there's essentially a shutdown mode. Also, when the shuttle docks, there'll be, of course, a jolt, and we don't want to be aiming at some star in a high accuracy mode when that happens. So the logistics visit every 90 days is a major occurrence on the space station. A lot of scenery can change, basic crew members will change, the scientists, the visitors, the payload people may change, and it may take some major part of the 7 to 10 day visit of the shuttle. And this would happen about every 3 months or so. Over on the lower right, you see the major outside operations facility. This is where things will be docked, assembled, repaired. We came to a conclusion early in the space station design business on this go-around that the outside operations, like many high-tech test facilities, are a major dominator on the scene. We don't want that facility anywhere but out in, quote, the backyard. We don't want it in the middle of things. We need a lot of reach room. We have to put utilities way out there. We have some hazardous units. The one that's on the end of a crane is about 7,000 kilograms of liquid hydrogen in that particular experiment. Well, there's major hazards associated with it, as those of you that have worked on major facilities that use cryogens here on Earth understand. In space, we don't always have these large cement block walls that we can put around them. So we have unique operations that and design features that have to be incorporated in that. We also need a major control center for all of the operations, and you see that mini blockhouse at the base of the crane that literally is a control center for everything that goes on in the aft section of the exterior of the space station. Meanwhile, in the other modules, things go on as usual on an interior basis, literally irrespective of what's going on the outside. Next one, please. Then we escalate our thoughts into major repairs and servicing of vehicles. We get into a hangar concept. We have to enclose some of these vehicles that we bring onto the space station and service. Some of them need major repairs. Some of them need major payloads exchanged on them, and we have to protect them from the sun. Sometimes we have to actually pressurize the area. So those of you that have been involved in large structures and hangar design understand what a challenge it would be to bring a major structure like this up, all folded up in the shuttle. I might mention I saw the truss work here outside. A major new thrust in our business is the development of efficient concepts for deployable trusses. I would say that anyone with good ideas in this area would certainly find it interesting to track what is happening in our business and could possibly even contribute to it. When you pack trusses into a high-density pack so that you can have a major deployment and expansive kind of set of structures that you see here, space frames, I believe they call them in your business, that is a whole new technology for us. big hooker in it is when you have lots of joints and you're trying to deploy it, you don't have a lot of capability to get out there and unfreeze a joint that may be hung up. And when you have hundreds of joints, you've got to make sure that the deployability is in fact there and that the reliability is there. So everything that glitters isn't gold in easily appearing to deploy structures. Next slide, please. I mentioned astronomy before. This is a view of what it might look like during the construction of this 20-meter telescope. 20-meter telescope will follow the current series of infrared telescopes and the space telescope that Lockheed is building, for example. Lockheed is building a telescope that is the size of the cargo bay of the shuttle, about 3 meters in diameter with its surrounding enclosure. The next step is this 20-meter set of optics. That'll be taken up. Each one of the individual mirrors, which are the hexagon shapes, they're being studied right now by Eastman Kodak and by Perkin-Elmer and the ITEC Corporation, the major optical companies in this country. And people like ourselves are studying the substructure. So there you see a unique blend of people that are optics-oriented, people that are structures-oriented, and our mechanical designers are having a field day designing these various deployable trusses. And our EVA specialists are, of course, trying to integrate the entire operation. sticking out. They want a design that keeps everything completely out of the view of the suffer back reflections of on the space station, turn it on, turn it off, perform some elemental and the old ones go down. Next slide. The habitation for each one of these crew people, of course, understand now, male and female, integrated facilities now, not so on Skylab. The personal hygiene functions, the waste management, 150 pounds for each crewman for 90 days, no small problem. Trash management, huge problem. A Skylab, we were fortunate, the Skylab was built out of an upper stage of Apollo. It had a huge liquid oxygen tank, did not have oxygen in it, but we used it for a trash bin, 22 feet in diameter and about 10 feet deep. Very convenient. We're not going to have that on a space station, but we're already noticing on Spacelab that we generate a tremendous amount of trash with the food, the cartons, with the paper that's involved, the throwaway clothing, reusable clothing, that type of thing. And getting all the way down to the bottom element, the most personal element, we feel a full compartment concept, not the crowded concepts that you sometimes see for a space station, that if they're going to live up there for long periods of time, the crew compartments should be fairly elaborate so that we don't end up with psychological problems on the part of these high-tech personnel that we have involved. Next slide, please. Here's an image of a central adapter. I'll go through several charts here just to give you an engineering description of these several modules that could be basic to anybody's space station. Here you have a central docking adapter unit where we have essentially a bathroom. We have various ports on which to mount modules on the upper, lower, and straight out the back, and also into the screen attached to the front. Here is also where we have our escape hatch, our EVA airlock over there on your right. That's an airlock that permits EVA crewmen, there have to be two at all times, one monitoring and one performing EVA functions outside the vehicle. Inside the vehicle you have a workbench and maintenance bench and suit repair facility. This unit also is heavily shielded and would constitute a safe haven in case of trouble on the vehicle. That's sort of a central facility that most every space station has got to have. Next chart, please. A view of an integrated dual compartment. There are actually two compartments on the opposing side, or half of this particular module. This could be called a habitability module or habitat module. You could perform some functions, probably only monitoring functions, not too much in the way of scientific experiments in the racks that you see over on the right side, and some small central control facility to monitor maybe one or two modules of the space station. You see very much kinship here to this design, except for the staterooms, to the Spacelab design. And you see the same diameter, and you see the same end cones, which are, you know, optimum angle for a lightweight yet pressurized, lightweight design for a pressurized cylinder. So there will be a fair amount of sameness. Underneath the floor, we'll probably have our trash compactors and various pumps and pipes and filters for the environmental control system, and that will also be true on the space station of almost anyone's design. Next slide. This is the logistics module that's brought up, in this case, 180 days, has interior storage for bringing up things that have to be in a controlled environment, and exterior storage for bringing up water or bringing down water. Understand now, in the early space station, we will not totally recycle the water. We're going to recycle hand wash water only, but bring back the water that's used for the hygiene, human hygiene, that type of thing. So we will end up in a water trucking operation until some advanced space station will actually recycle all water in the space station, and wastewater will be processed to the point where it's perfect enough to drink. Next slide, please. Now we come to Brand X. The boys across the water in the USSR have been flying one half of this vehicle since 1971, and last year increased the size of the vehicle, almost double in size, and added a multiple docking adapter in the center there for even larger growth. Have major plans, have a giant vehicle roughly in size to our Apollo vehicle, which we no longer have, model of which is sitting in a launch area, has already been detected by our military intelligence. Plan big things in space. all built on a very simple modular approach, the way the Russians have always done. Very little exotic designs, but just straightforward, plain utilization of space, not too many design awards. The people sleep in there like the older submariners did, literally over the torpedoes or crowded around the equipment. Not too many human factors awards, but they get the job done. And they've been using the same vehicle for years. Once they come up with a design, much like they do in launch vehicles, they keep building that same one over and over and over and utilize it. They put their money in what they do with it, not the carrier vehicle. The analogy I like to draw there is the DC-3 has been used, not just because I work for that company. The DC-3 has been used all the way up through Vietnam as a gunship. The DC-3 was developed in the 30s. It carried guns. They had these high-intensity Gatling-type guns that were very effective. It didn't make any difference that the airplane looked like a modern design. It's the function, the payload is what was important. They used DC-3s, and up until a couple of decades ago, they used the Ford trimotor down the Brazilian jungles. Very effective. They got the job done. So we believe that the space station needn't be high advanced technology to put the people there, that the money should be put in, as the Russians are doing, in the payloads. And payloads are expensive. And the payload community is our user. If we spend too much money on the space station, in the NASA budget, there won't be any money left for the payloads. So we're biting the hand that will feed us and back us. So that's a very important thing I'm sharing with you as far as the politics of selling a new vehicle. And you probably have analogies within your own architectural world. You make the building beautiful, design-wise, perform the basic functions of accommodation, but the money-making aspect of the building, if it's an industrial facility or a commercial facility, is something you better make sure you understand the numbers on. Otherwise, you may not get another contract in the business if that design is inefficient or proves to be inefficient. Next slide, please. So we have a few things to think about as we look at where we are, where we're going, where Brand X has been and where they're going. We are the greatest in manned space flight. The things we've done, going back from the shuttle through Skylab, through Apollo, were spectacular. The Russians are now starting to build a small shuttle. The Russians never had a Skylab. The Russians never had an Apollo. They do have their own vehicle that's been up since 1971, a relatively small vehicle. They're avowedly military. They make no bones about the fact they do a lot of military work. They do a lot of good civilian Earth resources kind of work. Many exciting, rewarding, commercially profitable things are in prospect on the space station, and they need the long-term presence of the most capable machine that we know of, and that's men and women. The human being performs functions that in a lot of cases we have not yet been able to automate, plus the fact that he or she think on the spot faster than many computers can really develop a capability for. The Russians have been up there now some 13 years. Hopefully that we'll have a space station by the early 1990s. Next slide, please. So we find ourselves, in closing, taking the perspective of being in orbit, imagining commercial activities producing pharmaceuticals, producing exotic metals, producing chip materials. We have an electronics explosion, gallium arsenide chips of very high purity, which means very high performance computers are better made, can be better made in zero gravity than here on the ground. So industrial use, major scientific increases in capability, major technological advancements made in orbit that can be used on the ground, major use of a space station as a space base for other things in orbit so the shuttle doesn't have to keep coming down to perform those functions. Those are what are in prospect for the space station. If I could have the last overlay. It's all because we now have what? We have unique access to an entirely new horizon or an area beyond a new horizon because we have the shuttle. And if we don't use the shuttle for anything more than just a shuttle for short-term operations, we're doing something akin to, possibly in the history of this country, of running back and forth to California from the East Coast and never staying and really doing very much and discovering this great state that we're a part of. Thank you very much. Are there any questions that I can try to answer? Yes, sir.
Could you briefly run down some of the environmental differences between living on Earth and living in a space station, conceptually, routine, daily?
In space, in zero gravity, you forget about your feet, number one. You're very conscious of your head and your upper torso. And on Skylab, there was such an intense focus on that, and maybe a little lower, but the feet essentially tore stuff off, tore cables loose, bumped into things and much more. That's number one. That's very personal. Secondly, it takes a while to figure out that you're really traveling with a fair amount of mass as you push off one side. And it doesn't take you too long to learn, as you go plowing into the other wall, that that's a problem. The operations of your experiments are such that although we design a thing for basic ground kind of racks and instrumentation panels and displays and what have you, yet you always see the astronauts in Spacelab in completely, disoriented kind of operations. That's going to take a lot of study, and there's a big interest growing now and big activity going up at NASA Ames. John, Tom Taylor, and I were just up there last year. Big consciousness of human factors in the design of a space station. We showed a mock-up we made for a space station design some 8 years ago where it doesn't look anything like the interior of Spacelab, but consoles go all the way around the interior. And we feel that that's got to be a value. We felt at that time that that was a very important new look as to orientation in a new and different kind of environment. But over and above that, people acclimate very readily. Another reason for staying up there a long period of time is a fair number of people have a few stomach problems for the first couple of days. But after that's ironed out, we have good experience after that.
What about the voice communication and light, the things that we're used to in a space like this?
Lighting, there's a fair amount of study went into lighting on Skylab, and use of colors, by the way, an extreme study on the psychological aspects of coloring and paneling and shading and what have you. Voice, I'm not aware of any problems, particularly in voice communications. Other than that, we didn't experience too many problems. I don't know whether I answered the basic thrust of your question. The human body acclimates, tremendously, they found, to these things. Plus, actually, there's some uniquely physical thrilling aspects, too, that without the dynamics of gravity plowing you back into the water after you jump off a diving board or something, or trampoline, we understand that the people up there really have a ball. There's some unique things you can do. It looks sort of silly, but they really feel very good. Yes? Big heat problem in the shuttle cargo bay. Never want to point the shuttle cargo bay to the sun too much. We build very special sunshades for stuff that is in the cargo bay, for our payloads and our launch vehicles that operate out of there. The materials will probably be heavily aluminum, graphite epoxy, that type of thing, and except for some degradation in graphite epoxy, some outgassing of moisture particular, but you can fix that on Earth by putting them in an autoclave and baking them out. Of course, then you have to keep them in something while you put them in the cargo bay and take them up. As far as the biodegradation of materials, that would only apply to those where it's specifically designed to probably take a change of chemical state or something like that, as in a major deployable sphere or something like that. Yeah, basically there's an easy out in the construction of a space station when the intention is that it will stay up there until it's brought back, hopefully in pieces or guided. You see, we intend to have, if it ever is brought down, it'll be brought down in a controlled mode, as opposed to, you know, that is now essentially range safety type policy, orbital range safety policy. But we don't need, obviously, all the reentry capability, because when we bring it down, it'll either be in pieces or it'll be controlled into an ocean setting. So in that sense, it's a completely different design challenge than the shuttle. One more question.
I have a question.
See, a hand and a voice is, gets attention more than just a hand.
Has NASA studied the possibility of using handicapped people in space, since the apparent use of the human body isn't really used in space, and that handicaps might find the environment more creatively than here on Earth? And if it happens, or if it has, is there any reason for not sending them into space?
If they're basically healthy, there is no reason. In fact, I would look for, you know, we're all aware of handicapped people that do spectacular things. I wouldn't be surprised, you know, except for certain cases where you'd probably see something like that. Certainly have people that are in science, heavily in engineering or what have you, that can perform some of those operations. But I think that certainly will come. You know, there even is talk of having burn centers in orbit, where unique type of zero gravity recovery centers are created. Certainly a major step short of that would be the type of situation you're talking about. Well, thank you very much for your attention.
Thank you, Fritz, very, very much. Our special guest here would be very happy to guide you all over to our exhibit. And I have just a couple of quick thank yous to make for the exhibit. We have a lot of fun with all this space stuff, too. I'd like to thank Andy Munson for his special work on the exhibit, Roberta Brubaker, Jim Busby, and Carlos Rocha for their work on the exhibit. It was kind of a quick job and a lot of hard work, but we're very proud of it. And I never trust these guys. And please just head on over to the exhibit, and thank you very much. And we'll be doing some more space programs in the future. Thank you.